Hello everyone, so welcome to the very last lecture for EECS3101. So today I just want to talk briefly about, well, I wouldn't say briefly, but thoroughly, and at least give you the proper intuition about the correctness of the Kruskal minimum spanning tree algorithm. We already traced the algorithm in the last lecture, if I can remind you, right? So that's what we did. We kind of started from the graph, and then try to build the minimum spanning tree using a table like this. So that's really the assumption I make about what you should really know before studying for this makeup lecture. If you haven't, please make sure you know how to trace the Kruskal's algorithm first. Okay, so I want to refer you to quickly about the slides. So I make some final extension for the slide for your exam. So this is the example graph that we solved together, and this will be the tracing table. So this will be the tracing table I will have to use throughout the makeup lecture. But there's one thing I want to explicitly mention, which I didn't really say in the last lecture. Okay, so whenever we are trying to have an edge that has the minimum weights that's kind of extracted from the priority queue, it depends on whether the corresponding cluster for A and B, if the cluster are not the same, we'll see later. This is called crossing the cut. That's what we will see a little bit later in this makeup lecture. But you just want to know, whenever we are trying to go across two clusters, they are not the same. In that case, it's called a tree edge. Tree edge in the sense that we are building a minimum spanning tree along the way, right? We are making one edge, like a one edge extension towards the final minimum spanning tree. On the other hand, if the two clusters are actually the same cluster, because you can see, for example, C and D, they are in the same cluster right here. In that way, we are not really making any new edge, but this edge here it's not going to contribute to the final minimum spanning tree. Okay, let me just show you very quickly from the diagram. Okay, so now if you look at, let's say, this one here. Let's say for BC over here, you can see BC over here. At the point we're considering for BC, B and C are in different cluster. In that way, it's so-called crossing the cut, what you'll see later. We're crossing two different clusters. In that way, B and C will be one edge to be included over here in the final minimum spanning tree. So that's case number one. So case number two, let's say in iteration number 4, we're considering C and D. At the moment, C and D are in the same cluster, right? You can see we already built minimum spanning tree so far. That's what we got. And now for C and D, it's really connecting from C to D in the same cluster. In that way, we shouldn't really connect it. Otherwise, we get a cycle for the minimum spanning tree, right? So this one here is called an internal edge. Okay, so that's what you will see on the table here. So you want to also distinguish between what a tree edge is and also what an internal edge is in the case of minimum spanning tree when we are building it. All right, so having this tracing table in mind, we're now actually going to talk about we're trying to build your intuition about the correctness for the Kruskal's algorithm. Before we study the cut property for minimum spanning tree algorithm, let's discuss 3 important definitions. So we're going to talk about partition, cluster, and also cut. Let's start with the definition for partition, and then we're going to go back to the tracing table for the example to really see exemplified what a partition can look like. So a partition, by definition, is going to be multiple pieces, and each piece is going to be a set of vertices. I'll write it down in just a moment. Let's just go over the bullet point here on the slides, and I'll switch to iPad. So it's going to be a set. We can use capital P to denote a partition, and it's going to be non-empty disjoint vertices set whose union equals V. Oh, we'll get there. Okay. So these are the 2 mathematical properties for what a partition should look like. So these are the definition. These are the operators that we actually have been using throughout the course. I'll leave it to you to really make sure you understand about how this formulation corresponds to the example which I'm going to discuss. So this one here is just the generalized union operator, which I'll briefly mention as well when I actually talk about the example. Right? I'm going to leave these 2 properties to you, right? Just using universal quantification and also the union operator. They're pretty straightforward to really see the connection. I'll leave them to you. Okay, so let's talk about partition very quickly. Okay, so partition, let's see the definition first. So partition, that'll be the first one to define. By definition, a partition is going to be a set of sets Okay, or put it another way, you can think about it's a set, and every member in the set is also a set. A set where each member is a set of vertices. Okay, it's a very important definition for you to actually understand, right? So let's now highlight this one here, and then we'll see example. Okay, it's a set where each member is actually another set of vertices. Okay, so you will see in the tracing table, this particular column here talks about for each iteration, we actually got some partition from each iteration. So you definitely got lots of examples from the Kruskal's MST algorithm. Let's take a look at some example just to begin with. You can see in the very initial iteration, you can see this is the, oh, actually this will be the initialization stage, beg your pardon. It's not even the first iteration just yet. So even before the first iteration, we want to do some pre-processing, like a preparation work for the algorithm. So this will be you can think about every vertex is its own set. Okay, so you can think about right here. So this will be a set. You can think about this is the set of sets, where every set over here is by itself. You can see 1, 2, 3, 4, 5, 6, 7, and 8. You can see for this particular partition is a set where each member is a set of vertices. So here, this is just a singleton set of vertices. This is just another singleton set of vertices. Okay, again, partition is a set where every member is also a set of vertices. Okay, let's see just one more example. If you look at maybe the last iteration, okay, if you look at the last iteration, which will be iteration number 9, right here. So for this one here, you will see that we still have a set right here where there's only one member in this particular partition, right? That's why in the definition that you will see that it contains one or more pieces. Okay, it's important to see that you can either have one member set or you may have multiple member sets. Okay, so here the only member set you have is just this one here, just this one. Okay, so that's the only one member. Okay, so if you like, you can think about this is only one member in the partition, whereas right here, how many members do we have? Right, we can count very easily, right? So over here we got 1, 2, 3, 4, 5, 6, 7, 8, exactly the number of vertices in the graph. So we got 8 members in the partitions. Okay, and then let's now see if there's anything else about partition. Okay, yeah, so you can see here we also say it's a disjoint, right? So every member in the partition must be not empty. So you cannot really have an empty set as a member in the partition. That one should be obvious. And also between the members in a partition, they must be exactly disjoint. Okay, so let's talk about this one here. That one will be easy to see. You can see these two. So these two members, they do not overlap. And also you can see these two members, they do not overlap. And also these two members, they do not overlap. If you choose pairwise the two members in a particular partition, their contents should not overlap, meaning that their intersection should be empty. Right? Just see one more. You can see these two members, also they are disjoint. They actually do not overlap. Okay. All right, and also the union of all the members in the partition is going to be equal to exactly the entire set of vertices. What does that mean? Okay. So here, if you think about, if I apply the generalized union operator, okay, that means I want to union this with this, with this, with this, all the way, right? If I want to reunion all these sets together, what would that be equal to? It will be equal to exactly all the vertices in the graph, which will contain A, B, C, D, E, F, G, H. Okay. So you can think about, if I try to generalize union, if I say there's a generalized union operator, that will be exactly equal to all the vertices. Okay. Similarly, if I try to do the generalized union over here, there's only one member, but that's okay, right? So that's also equal to all the vertices. Okay. If you also do try to union all the members over here, right? altogether is also equal to V, right? Okay, I think just writing these two down will be enough. All right. So now we basically cover all the essence about what a partition is. Just remember, it's going to be a set of sets of vertices. So it's going to be a set where each member is a set of vertices. Okay, and also between any two member sets, the contents must be non-overlapping. The intersection must be empty. All right. So let's now switch to define what a cluster is. Okay, so by definition, a cluster is simply one single piece in the current partition. So remember, each iteration in the Kruskal's algorithm, in each iteration, we actually got one particular partition. Of course, the shape of the partition might actually change between iterations. Each piece or each member in a partition will be called a cluster in the Kruskal's algorithm. So you think about partition over here. Also, later we're going to talk about what a cut is. Partition and cut are the more general concept beyond any MST algorithm. But when we talk about cluster over here, the middle definition here is more specific to the Kruskal's algorithm that we kind of spoke about in the class, right? So let's now write something down. Okay, let's see. So in each iteration of executing the Kruskal's algorithm, so we're gonna see exactly how it's gonna change. But before that, let's now write some definition, okay, quickly. So the second definition will be about what a cluster is. So here we got a cluster, okay, cluster. And we somehow already kind of indicated earlier about what a cluster is, just without mentioning its name. Okay, let's see what a cluster is. Okay, a cluster by definition is simply a set of vertices. A set of vertices. Okay, basically it's a member, it's a piece or a member. A piece or member of some partition. Okay, so for example, you can see that in the initialization stage. So here we got 1, 2, 3, 4, 5, 6, 7, 8 clusters. And in the final configuration over here, we got a single cluster which contains everything. And of course, in between, we got every iteration over here. We just got different number of clusters, right? So that's basically we're moving around. Well, not really moving around. We are basically merging clusters whenever we can. You can definitely refer to the algorithm to see how we trace it last time. Okay, so let's now write down some observation here. So this will be the initial configuration before any iteration. You can think about in the initial partition. So each vertex in its own cluster. So you can see over here, this is the partition in the initialization stage. So you can see each vertex. Vertex A is its own. It is in its own cluster, and vertex B is also in its own cluster, and etc. But in the final configuration, it's kind of the opposite. The final iteration, so all the vertices will be in a single cluster. That's where we know that we should really stop. Okay. So this one here in the final partition. So here we know that all the vertices in a single cluster. All vertices in a single cluster. Or if you like, also something we kind of noted earlier, you can think about this cluster over here. The contents of that is exactly equal to all the vertices. That's a special case. Okay. All right, let's now go back to see. Okay, now in each iteration, okay, so let's say we got x and y, like a two vertices, okay. So a cluster is simply a set, is a member of, okay, that's something we said, for example, you can say the cluster for A in the initialization is this cluster, and the cluster for A, okay, let me just write down. You can see that somehow the cluster may grow, but it may never shrink. So you can think about this one here. Okay, So this is the cluster that we can, let me just focus on A, okay? You can just see how the cluster may actually evolve over time. So this is the cluster for vertex A. You can think about the cluster or the set that contains A. And then this is the cluster that contains A after the first iteration. Obviously, you can see that that one actually merged A and B. So that's why it has grown. So this is the cluster of A. Okay, so you can think about it now in another iteration, it keep growing. It never shrink because we always try to merge two clusters whenever we can. So over here, so this will be the cluster of A right here. But sometimes it might be possible that there's no change, in which case the cluster for A will remain the same in between these two iterations. Right? Hopefully that makes sense. All right, so just it's very important for you to really build an intuition, build an understanding about whenever you're referring to maybe some vertex, you want to find out what's really the cluster or the set that contains that particular vertex. So if I give you G over here, you know that the cluster that contains G is right here. On the other hand, if I ask you about G in this particular iteration, the cluster that contains G is this particular cluster. All right. And then the next point. So here we say line number 10 and 11, we can refer to these two lines. It's just about the cluster for U and cluster for V. It's like an X and Y over here, right? Just the same idea. I'll leave you to look up the algorithm. All right, so now these 2 points, okay? So these 2 points are not difficult, very straightforward. Let's talk about the first one. If somehow these two, if two vertices X and Y, they actually have the same cluster. For example, you can see that I got B and C. So these two are in the same cluster. What does that mean? That means so far we have built already edges that connect between all these vertices. Let's say A, B, C, D, right? Iteration 5. Okay, let's just go there very quickly. So if you go here, this is the tracing we did earlier. So iteration number 5, right? If I look at, let's say B and D, right? You can see so far A, B, C, D, A, B, C, D, so far they have been connected using 1, 2, and 3 edges. So this form are connected components. And since A, B, C, D, all these vertices actually have the same cluster. So that's why we said all these vertices are in the same connected components. Okay, so let me just go back there and then write it down. So for example, you can see that iteration 5, okay, let's say just for B and D, right? You can see over here B and D. So their cluster is the same because they simply refer their cluster simply refer to this particular set right here, right? You can say cluster of B is just the same as the cluster of D. So that means they are in the same connected component. Again, the same connected component because A, B, C, D at the end of iteration 5 right here, we actually got A, B, C, D. We got 1, 2, and 3 edges connecting them. So that's why they are part of the part of one connected components. Okay, so when you maybe try to retrace this particular example here, you want to really see how we build up the connected components. You can think about in the beginning we got 1, 2, 3, 4, 5, 6, 7, 8. When we say 8 members, you can think about we actually got 8 connected components. On the other hand, when we say 1 member over here, we got a single connected component, which makes sense because eventually we want to build a minimum spanning tree. A spanning tree, of course, should represent a single connected components. Hopefully everything can connect right now for you. All right, so the second case will be, let's see. So go back to the slides. The second case will be, what if the 2 vertices belong to 2 different clusters? Well, obviously that simply means they are not in the same connected component. Let's see, example. We still choose iteration 5, let's say. Okay, so here, let's say you choose, let's say F over here and also G over here. They are in different cluster, obviously, right? So here you can say, because these 2, the cluster of F, which will be this cluster, and the cluster of G will be this cluster, is not equal to the cluster of G. So that would mean they actually in different connected components. Okay, let's see if we can see that from the diagram. Okay, so we talk about after iteration 5, we got we got F and G. Okay, so after iteration number 5, you can think about F and G. So we haven't really got this one here yet. So this edge is only connected in the later iteration. So at this point, F is in its own connected component, and G here is also in its connected components. Later on, we're gonna use this particular edge to connect these two, to make it, to merge from two connected components into a single one. But at the timing of iteration number 5, F and G, they belong to different clusters, so they are in different connected components. Later on, they will be connected using this edge at the end of iteration 8. All right, right. Very important to see such observation and insights about this algorithm over here. Okay, all right. So that's about cluster. Let's now move on to the last definition, which is about what a cut is. You can think about it's it's more like a special case for partition where we got exactly 2 member sets in the partition. However, I want you to watch out right away. You can make a notes. When we say a cut has only 2 member sets, like 2 pieces, you don't necessarily always have the cut contains exactly 2 clusters. So here we are trying to distinguish between one member set in the partition versus a cluster that may be a member in the partition, right? Be careful. I'm gonna illustrate to you. Okay, let's now see exactly. Okay. So what a cut is. Let's now start with the most basic stuff, which is the definition. So a cut right here. Okay, so a cut. I'm kind of running out of space, but let me put a star over here. Okay, and then I'm gonna write it elsewhere. Okay, so a cut is really just a special case. A special case of partition. It has exactly 2 member sets. 2 member sets of vertices. And there are 2 cases I want to actually show to you. When we say 2 member sets, okay, it may be that these 2 member sets just happen to be 2 clusters, but in general it may not be. Okay, so it could be these 2 member sets may be exactly 2 clusters. Okay, or it could be a little bit more general. It could be one single cluster versus all the other vertices in the graph. Okay, well, it could be one cluster versus the rest of vertices. Okay, so what do I mean by that? Okay, let's start with case number 1. It's actually easier to see. Okay, for case number 1, when I say we got exactly 2 clusters, and for that one there, you can just look at iteration number at the end of iteration 8 right here, right? So over there you can see number 1, we got a partition right here. Partition and partition. And here we got exactly 2 clusters. One here, and also the here. So this is kind of the second last iteration where it just happened to be a cut. So this would be more like a narrow sense to see what a cut is, but that's not general. But you know, it's a cut, right? Nothing wrong with that. So this one here is a cut. So this is a partition and also happen to be a cut. Again, it's a cut because this partition over here got exactly 1 and 2 member sets, and each member set just happened to be a cluster itself. All right, so that's case number 1. Okay, what about case number 2? So for case number 2, we have one cluster and also the rest of the vertices. So how do we see that, right? So let's just take one iteration, for example. Let me just choose a different one. How about at the end of, let's say, iteration number 5, right? That one is a bit too messy right now already. Well, a little bit too crowded. Why don't I say just right here? Okay, so here you can see that we got basically, how many clusters do we have? We got 1, 2, 3, 4, 5, right? If you only look at a cluster themselves, this partition here is not really a cut, right? If you only look at that. Okay, first of all, if you look at just this partition here is not a cut. Because we got the partition over here, we got 1, 2, 3, 4, 5. We're not getting exactly 2 member sets, so that's not a cut, right? It's a partition, but it's not a cut. However, it is possible to interpret this particular configuration over here in a way that we can interpret that as a cut. So this will be the second way, which is more important when we actually talk about the cut property, and also to see the intuitively why the Kruskal's algorithm is actually correct, right? So the second way is to see, we simply consider basically just the one particular cluster here. You can choose any cluster you like. Let's say I choose A, B, C, D, and also versus the rest. Okay, so think about this is the cluster of, for example, let's say the cluster of B, right? So let me just choose B right here, right? That's the cluster which B, vertex B belongs to. And you can think about all these vertices, that's the rest. You can think about it's more like a complement of the cluster of B. So this is more like all the vertices set minus is like a set difference, the cluster of B. So what do I mean? So this operator here is just about set minus, like a set difference, which you learned from the previous math course. So all the vertices V here will be A, B, C, D, E, F, G, H. I'm saying that take out A, B, C, D, which means I got E, F, G, H, all the rest. So now let's visualize this a little bit, okay? So this one here, the way to visualize it is, let's say we start with A, B, C, D, okay? So we can think about A, B, C, D, A, B, C, D, okay? So this would be the cluster of B. Of course, you can say that this is also the cluster of A, cluster of C, cluster of D, right, as well, right? It's their equivalent, okay? So let's say we talk about this cluster over here, but for the rest of the vertices, we should talk about them as a single set. We're not really talking about cluster over here. Cluster, again, is a concept very specific to the current algorithmic configuration for, how we construct the MST, ultimately. Okay. So here you can think about right here, the big set over here is the V, which contain A, B, C, D, E, F, G, H. So the rest is E, F, G, and H. Okay. So you can think about all these E, F, G, H. Okay, let me use a different one here. Okay, we got E, F, G, H. So all these together will be all the vertices set minus the cluster of B. All right, that's also very important for you to see. And then let's say, for example, okay, let's look at a different iteration for illustration. So let's look at iteration number 6 right here, right? Let's revisit very quickly about what iteration number 6 will do. Okay, so iteration number 6 over here. So in the beginning of iteration number 6, we started with this particular configuration. After that, at the end of iteration number 6, this is what we get as a result, right? So we basically transforming from this partition into this partition, right? So for this particular partition, you can think about we got A, B, C, D, right? And also to really form a cut, we simply think about all the rest of the vertices are right here, E, F, G, H, right? A, B, C, D, and also the rest. The algorithm will actually use to really connect D and E. Cluster-wise, it's really trying to merge this one here and this one here, so that we actually got this cluster, right? That's something we know pretty well. But let's now think a little bit more abstractly. So what we're doing is we're trying to connect an edge that contains the two endpoints, D and E, right here. Okay, so D and E over here is actually going to connect two different member sets in some partition. Okay, that's why it's a cut. So you can think about here, we got D, right? You can see D is right here, it's in cluster of B. And then we're connecting that to something that's outside the cluster, right? E. And we are trying to connect them all together, right? Right here. Okay, let's now try to make some annotation just for this part over here, right? It's important for you to see that we got D here, we got E here. They belong, D is in one cluster, and also E is simply outside the cluster. That's the way to think about it, right? It's a cut. And then what can we say about this edge? So I'm gonna write it down here. So you can think about the edge, DE. So the way to actually say this is it will crosses the cut. The cut. So it's a very special term you have to also get to. Okay, so if you look at the slides, so if you actually got a cut, for example, this could be the cluster of some vertex. In our case, it's the cluster of B and also the remaining part. And if we got exactly these two member sets, you can say that the partition itself is a cut, right? That's a definition. So in our case, we got exactly the cluster. We got exactly the cluster of B and also the rest, which will be E, F, G, H. And now this particular edge, we say that it crosses the cut. Okay, so that's the definition I want to show to you, the term, right? We say an edge crosses the cut if the endpoints, one of them is in one set and the other one is in the other set. You can think about the two endpoints, D and E. D is in one set and E is in the other set right here. So we say crosses the cut. Right? So that'll be the final definition you have to also understand first before we can move on. All right, so far we talk about three very important definitions about partition, cluster, and cut. So, and then the next stage will be to really talk about the cut property. Let's now first go over the written definition for the cut property, and then we're going to visualize it to make it a little bit more intuitive for you. And then I'll try to also make some concluding intuition just about how we can connect this cut property to the Kruskal's algorithm before we kind of get into the more details about the connection. Okay, let's do one thing at a time. So the cut property, let's read it together, and then we're going to visualize it. So what's the cut property? So cut property here is not just for the Kruskal's algorithm, it's for any minimum spanning tree algorithm that's kind of designed using the greedy method, right? You can also revisit about what the greedy method's ingredients are. So we are given a graph which has weights on the edges, and also the graph is connected. Well, because if the graph is not connected, there's no minimum spanning tree. There's no spanning tree even. And then we talk about any cut. Any cut you can actually find, basically you just find a non-empty set of vertices that will be S, and then the rest of the vertices will just be the difference between V and also S. So if you look at these two groups or sets of vertices, it's a special partition with only two member sets, and then you say that there's a cut. Given any cut, if you somehow can choose an edge, we call this edge E, and there are many edges that can go outside the member set S to really connect to something that's outside S from certain vertex. I'll show it to you. But among all these crossing edges, so E is the minimum one, the one with the minimum weights, right? So this is very important to see E is a minimum, and this is a conclusion about cut property. If you got all these three conditions actually given, so you can say that the E here must be part of the minimum spanning tree somehow. Okay, so there will be some minimum spanning tree, because the number of minimum spanning trees from any graph that's connected may not be unique. There might be multiple possible spanning tree you can draw, but we're saying that if you're able to get E over here based on the above three conditions over here, it's guaranteed E should be a member of some minimum spanning tree. So this is a very important actually property to actually know, but it's only about definition, right? So I'm gonna visualize it and also tell you what's the most intuitive consequence that we can draw from there. And we also say that E is said to be and safe edge for some minimum spanning tree. All right, so that's the safe property, right? So you can definitely try to also read over the written definition more carefully and also try to visualize it yourself too. Okay, let's now talk about visualization. Okay, let's start from scratch. So number one, we know that we're talking about the condition number one. We're given a graph G. Okay, so let's say just draw in the abstract way. So, you know, a graph will contain vertices and also edges, right? Just a collection of all the vertices and edges. So let's say we got right here. Okay, so let's say here. So let's say this one here, this big collection over here is the G. Okay, so think about this one is the graph with all the vertices and also edges. Okay, and also it must be weighted. Okay, and also it must be connected. Right, it's basically condition number one in the written definition. Okay, and then we're talking about any cut. You can create a cut as long as you can find a non-empty set of vertices. It's called an S. Okay, so what I would do is I'm going to find some non-empty set. Okay, so this will be some, let's call this S. So you can think about this more like a non-empty set of vertices. Of course, the smallest S you can get is one that contains only a single vertex, a singleton set. Okay, and then so that'll be the and then we got a cut here, and also the rest. You can think about this will be S over here, and also the rest, right? So now, how do we see a cut? Okay, so now you can see that we say there's a cut. It's going to be a partition with only two member sets. So we got S, and also we got V, set minus, set difference, S. So you can think about these are the two member sets of the partition. Right? So these are the two member sets of the partition. Okay, if you recall the definition we just spoke about, cut is a special partition with only two member sets, right? So as long as you can find any S that's not empty, you can always find out a cut accordingly, because the set here will just be everything else. All right, so let's now say the third components, and we say that E is a minimum weight edge. Okay, so let's say this. So let's say there might be different edges, right? Say, for example, there might be some vertex over here, and then it might connect to some vertex that's outside S, right? This can be one edge. There might be another one here, and that one may connect outside. Okay, and also there might be another one here. You know, you see my point. There could be as many as possible, you know, depending on the example graph you're given. So let's say here we talk about edge E right here. All right. So number one, E over here, we say that it cuts cross, actually crosses the cut. Okay. So because you can see this, you can think about this one here, this endpoint, and also this endpoint. One of them is inside S, the other one is outside S. So let's write it down. So this endpoint here is in S. This one here is not in S. Or you can say it's actually in the set difference between V and also S, right? So these are equivalent, right? I'm just manipulating the symbol like a set operations, okay? And then we'll say that amount. Let me just refer you back to the written definition very quickly. So we say that among all the edges that cross this cut, E is the one with the minimum weights. Okay, so among all the edges, 1, 2, and 3. Let's say we only got 3 right now. It can be as many as necessary, well, as possible, you know, depending on the application. So 1, 2, and 3. Among all these 3, this one here has a minimum weights. So you can think about right here. So E here, among all edges crossing the cut. And when I say the cut, over here, I'm really talking about the cut right here. All right, right here, right? Just to know that we're talking about the same cut right here, right? So this will cut through the cut. This will go. This will cross the cut, and this will cross the cut as well, and this will cross the cut as well. Okay, and this one here has a minimum weights. All right, and I can also even make it even more explicit. E is the weight of E is larger than. It's actually smaller than. Sorry, beg your pardon. It should be smaller than because it's a minimum. The weights of all other edges crossing the cut. Yeah, basically minimum weights. Okay, let me just write it down. So that one there has the minimum weights. We're only talking about edges that will actually cross the cut. For any edges not crossing the cut, we don't care at this point, right? So E happens to be the minimum. Okay, so now what's so special about this one here, right? So you can see right now we talk about all the three conditions, right? We talk about the input graph, we talk about any cut we can actually form, and we talk about for all possible cuts, for any possible cut that we can form. And then we also talk about the minimum edge E. So there is a minimum spanning tree that contains E. Okay, so you can actually think about this particular edge over here, right here, just this edge. This edge is actually guaranteed to be the edge of some minimum spanning tree. We don't know exactly how that minimum spanning tree ultimately will look like, but we know for sure E will be part of it. Okay, that's kind of the beauty and powerfulness about this cut property. Okay, so here, okay, let's now write this down. So there is an MST. Let's call it T because that's the T we actually use in Kruskal's algorithm, such that E is actually a member of T, right? You can think about, for example, if you look back to the Kruskal's algorithm, so T here actually contains only E1, right? You can see E1 is actually this edge over here. And also T over here contains E1, E2, and E3, which will be E1, E2, and E3, right? Etc. Right? That's what we meant. So we are representing the minimum spanning tree by a set of edges, okay? Such that. And we also say that E is a safe edge. Okay, that's something you will also see on the slides. It's a safe edge. Okay, you can see that. Let me show to you on the slides. You say that it's a safe edge for some minimum spanning tree. Okay, so now how? Well, that's a cut property, right? So of course you're gonna revisit the visualization and also try to understand the written definition. But let's see why this cut property will be crucial for the Kruskal's algorithm. So in this course, we will not really try to prove the Kruskal's algorithm formally for its correctness, but I think the cut property here is very important to actually kind of see intuitively why it is okay to really keep selecting the minimum edge, and then somehow the minimum spanning tree will just be obtained or be reached ultimately. It seems to be magical, but it's not really. So the cut property here is really the foundational property that will guarantee the keep choosing the minimum edge is going to work. Okay, let me write it down. Okay, so what we have is, so Kruskal's algorithm That's the only minimum spanning tree algorithm we cover in this course, but there might be others. Okay, so we say that keep choosing the minimum edge. Okay, let me just show you one very quick connection, right? If you look at the algorithm over here, right, you can see that we keep choosing something back from the priority queue, which is guaranteed to be the minimum, right? Because we're using the edge weights as the key. Keep choosing the minimum, and every time, so we somehow will try to merge the two clusters, and then the reason that we can merge the two clusters is because we're trying to use an edge to connect them. And this edge is a minimum, and that one guarantee is going to be a member of the ultimate minimum spanning tree that we're going to build. We don't know exactly how that minimum spanning tree will look like at this point of iteration, but we know that UV guaranteed to be there. Okay. It's a very powerful property, but could be a little bit abstract in the beginning, right? So that's why it takes some time. The minimum edge to merge clusters. That's basically what the iterative algorithm will do. It is safe to assume that eventually a minimum spanning tree will be obtained by the algorithm. Okay, a very quick recap, and then we try to do a little bit more insights into this cut property and see its correspondence to the Kruskal algorithm. Okay, so here we say that we start with some graph with the weights, and also it's connected. And in order to really find a minimum spanning tree, ultimately, we want to say that whenever we can find a cut, so a cut is going to contain some non-empty set of vertices and also the rest, right? That's the cut. If for all those edges that will actually cross the cut, which will go from S to somewhere else outside S, right? From S into somewhere outside S. If E is the crossing edge with the minimum weights, it's guaranteed E here is going to be part of some ultimate minimum spanning tree that we want to obtain, right? We just don't know exactly how the minimum spanning tree T will actually look like, but at least we guarantee E should be part of it, right? So keep doing this, and guaranteed by this property here, eventually we can get a minimum spanning tree that we want to find for the algorithm. All right. So try to look at the visualization, try to look at the definition, and also try to see this intuition line here, and then we'll try to go over exactly how the Kruskal algorithm in certain lines, how that can be actually be connected to this cut property. So we're going to look at some critical lines in the Kruskal algorithm and see how we can try to understand the cut property a little bit more, and also the relevant components in the cut property. Okay, in the Kruskal algorithm, I'm going to refer to the different line numbers in the pseudocode. You can also refer to that as well on your notes. Let's look at line number 10. In line number 10, we are actually talking about the cluster containing vertex U. And then we try to see how can the cut be formed accordingly, right? So we talk about as long as one of the set is actually non-empty, then you will be able to form a cut accordingly. But you gotta be careful about some edge case, which I'll mention as well. Okay, let's see the first point, line number 10. So line number 10 is here, right here. Okay, so we talk about the cluster right here. Okay, the cluster U over here, and then this line, of course, this line here is going to be executed for every iteration. So let me just try to find out maybe 2 iterations to show to you the idea. Okay, so we're going to see how the cut can be formed, and also we're going to see how the edge that we kind of choose as the minimum is going to cross the cut. Let's see how that's going to happen. So let me first of all look at iteration number 1. So iteration number 1 right here. Okay, so for this iteration here, that one there is actually going to choose the minimum edge AB. Okay, but let's see how the AB can be understood right here. So in the beginning of iteration number 1, we're going to get this initialization, right? So that one there, you can think about we got basically 2 parts. One part will be just the cluster A. Okay, so you can think about A here. So that will correspond to the cluster containing A. And also the second part will be just the rest of the vertices. So that'll be the part that contains B, right? So you can think about the rest is simply just contain B. Okay, so that will be one cut. So let's write down the cut right away. So this one here actually got the cut, which got exactly 2 member sets. So we got A and also the rest. So I'm just gonna say V. So we understand that V will be all the vertices A, B, C, D, E, F, G, H, all the 8 vertices. Set difference, the A, right? Right. In this, it's also important to actually note this one here. A here is the entirety of the cluster containing A, and also this one here happen to also contain B over here. Right? You can think about, so again, that's why I said in the earlier that you should really try to distinguish between clusters and also the member sets in the partition. So they are not exactly the same. So once again, in this case, we got 1, 2, 3, 4, 5, 6, 7. 7 are the cluster. However, all these 7 clusters are understood as the second member set in the partition. Right? So you gotta really distinguish between these two concepts. Okay. So here you can think about the cluster of B is simply contained within this big set over here, right? You can see B here is simply one of the members right there, all right? And then what we're doing is we are trying to connect the edge AB, right? So AB here is going to cross the cut. So that one there, so let me just see here, because we know that they're cluster A and cluster B, they are different cluster. So that means we are doing the cut, all right? So actually, so for this one here, this will be star. Okay, let's now write it down over here for star. So merging, so we are going to merge in the first iteration, merging C of A and also C of B, right? Because now we are trying to merge the 2 cluster A and B. And then we got this, right? We can merge that because AB crosses the cut. Okay. So hopefully you can see that, right? So we are really saying that. So whenever you can discover that actually the edge that happen to be the minimum, if that one there is gonna cut across, well, it's gonna cross the cut. And the cut is actually formed by the cluster of A and also the rest, which guarantee to contain B. If that's the case, in that case, we can actually say that we can just merge the 2 cluster. Okay, let's do one more. Okay, so let's now talk about the second iteration. Okay, at the end of the second iteration, we're actually going to do this edge over here, right? That one's like a new edge that's going to be contained in the minimum spanning tree. Again, so let's now try to say we got B here. So we got B here, which will be this cluster, right? That's a cluster containing B. And also we got the rest. In that way, we can form the cut. So the rest right here. Okay, so let's now write it down. So here, because we know that the 2 clusters, they are different, that means by using BC as an edge, we're actually going to go from one set into another set in the partition. That's, you know, in the cut. So that means we're really crossing the cut. Okay. So one thing to really that's very important to note, whenever you see the inequality right here, inequality means we are trying to cross. But we'll see other cases where if C and D already in the same cluster, in that way we are not really crossing the cut. In that case, we cannot really merge the cluster, right? Okay. So whenever we actually got a cross, that means we can merge. That means we can merge. Okay. So let's also write this one down. Okay, just see what a cut is. Think about the process, the steps over here. First of all, given the edge that we have chosen here, B and C, you try to form the cut accordingly. So find out the cluster for B and also the rest of the vertices, which will guarantee to contain C. And then these are the 2 sets. And then you're trying to see whether you're actually going from whether this edge actually is going to cross the cut or it's not going to cross the cut. If it is going to cross the cut, in that way we're going to merge the cluster. Okay. So this one here is going to be, so you can see the cluster of B in this case is going to be AB. Okay, and then the rest V set difference AB, right? And this one here, we can see this is the cluster of B, and somehow the cluster of C is just contained within the rest. So that means this edge over here is going to cross, right? It's going to cross the cut rather than just staying within or internal within a particular group. Okay, so that one there, we're going to say star star. Right, star star is referring to this second inequality, right? So we're going to say merging the cluster of B and also the cluster of C. We can merge them because it's guaranteed we're crossing between this and also this. So these are two distinguished member sets. How do we know? Because we got this inequality over here. Okay, because BC crosses this particular cut. All right, so now I'm just giving you two examples of the cut, of the crossing the cut. But you can definitely try to find out other cases where you will see tree edge, right? Whenever you see any tree edge, that means we are really taking the edge that crosses the cut. But for internal edge, in that way, we're not really crossing the cut, right? As simple as that. All right, so that's about really the first point right here, right? About the forming the cut. And there's one special case I want to talk about, but also very briefly, right? Because we say that the cut is a partition where you got two non-empty sets, they are disjoint. So that means both sets must be not empty. So if you look at the last iteration over here, there's no way to form a cut from this one here, right? So that's also some edge case you want to watch out for. Okay, so you can think about iteration number 9. That's the last iteration, right? And then you want to think about this one here is already V. So there is no cut that can be formed from this particular configuration. Because if you try to say I choose this cluster here, which will be in the entirety of V, but V actually set difference itself is simply just going to give you the empty set, and we know the empty set is not allowed as a member set in the partition. All right, let's now go to the next critical line of the algorithm, and this might be the trickiest one to really to see that the first time, but it's not too bad. I will give you definitely some example, but you should really also try to think about it a little bit more, and also to find out other instances of the same point in the same tracing table. Okay, that's something I'll leave to you, but let's now talk about this one here. So we talk about line number 12. Okay, line number 12 is right here. Okay, let's highlight it first. Line number 12. So I have, let's use orange. Okay, so we got line number 12. Line number 12 is when we actually know that the two vertices of the U and V, right? You can see U and V is the minimum one that we kind of get from the priority queue. And we find the corresponding two clusters, and then we look at the two clusters are not the same. That means this edge, UV, is going to cross the cut, right? As we said earlier from the previous point, okay? So given that this is actually different, so now we can say something a little bit deeper, okay? Let's see. Let's see over here. The two clusters, the intersection should be empty, and also one cluster, well, think about we kind of fix C of U first of all, right? The cluster for U, and then the rest will be V set difference of CU, and that one they should really contain the other cluster, right? Remember, again, we talk about the member sets in a partition are not exactly the same necessarily always to just clusters, right? That's something we kind of spoke about earlier in the lecture, but that's something you can review. Let's now verify this, right? Let's choose a particular iteration for our illustration for this tricky point. So I'm going to choose iteration number 6 right here. All right, iteration number 6. And don't forget, for iteration number 6, the beginning of that would be the end of iteration number 5, right? So we look at this one here to consider for iteration number 6. After connecting this edge, we're gonna get this, right? Just don't forget the order, the timing. Okay, so let's now look at iteration number 6. And for that one there, we are actually going to look at this part over here, right? That's the beginning of the iteration number 6. Think about it as a pre-states for iteration number 6. Okay, so let's now make some annotation. Okay, let me just try to do a little more gently over here. Okay, just right here. Okay, so right here. So we say in the beginning of iteration number 6. Okay, specifically we're looking at this particular partition to deal with. This partition was a result from the end of iteration number 5, right? We're considering that right now for what we should do for iteration number 6. And cluster for D over here, you can see that will be the cluster for D, right? You can see D is right here. Cluster for D will be containing A, B, C, and D. All right, and then you will see that for the rest of the vertices, which will be E, F, G, H, right? So all these together, right? So you can see E, F, G, H, and also A, B, C, D. So these two are not overlapping, right? And you can see that over here, also for E here, E will be in this cluster. This cluster EF is exactly, okay, so maybe I can just do a little bit more for you, okay? You can think about the C of D intersection with all the vertices, set difference over here, the cluster of D, that one there is empty, right? And also the second one, since we talk about E here, will be the second vertex to talk about. The cluster of E is exactly part of the remaining, like the second member set in the cut. Okay, so think about these two equations over here, 1 and 2. So these two correspond to exactly what we got right here. Okay, and let's now move on. Okay, and then we say the edges are extracted in a non-decreasing order, right? So how do we see that? So it can non-decreasing, meaning that it can be either the same or increasing. Okay, so you can see that these are all the edges we kind of extract, right? In the different iteration, you can see non-decreasing, 1 and 2 and 3 and then 3 and then 4, right? So if you like, you can simply see all these are extracted in non-decreasing order. Non-decreasing order. Okay, that one should be also obvious. Okay, that's the nature of the priority queue. We just keep extracting the minimum. And then the clusters only merge and never split. That one you can also see, you can see the only line that's about changing the cluster structure for each iteration is about merging. We never say we have to split the cluster, maybe from cluster U, maybe two different subclusters. We never do that. So the only way you can actually modify the partition structure is by merging the different cluster. Okay, now that one is also quite straightforward. And now this one here will require a little bit of thinking, but of course most of the thinking will have to be done by you, but I'm just trying to help you. Okay, so now let's see this. We are now trying to talk about the cluster U. All right, so you can think about the cluster U, in this case will be the cluster D that we're talking about, right? You can think about from line number 10, we got cluster U and V, which will be U and V. So now D and E, so you can think about D here is like the U over here, okay? So we talk about the cluster D, okay? So cluster D is exactly this, all right? I should remember that. So any edge with one of, you can think about X over here can just be either just one of the endpoints, right? To make it a little bit more general. Any endpoints that's in the cluster of U, right? So that means any endpoints, so you can see the cluster of D is actually A, B, C, D. All the edges with one of the endpoints being either A or B or C or D. So that means they are somehow involved in this particular kinetic components, A, B, C, or D. And we say that if their weight is actually smaller than the current UV that we are looking at. So what do we mean by that? Okay, so I want you to look at this. Since we know that it's going to be non-decreasing order, in order to find any edges with a smaller weights than the current one we have found for iteration number 6, they must have already been found right here, right? So let's look at them right here, okay? So first of all, let's now just highlight all of them. So you can see 1, 2, 3, 3, 4, right? You can see all these all these edges have the weights smaller than the 5 right here, all right? So now we can say for all these edges, if one of their endpoints is either A or B or C or D. Let's highlight them, right? What are they? So you can see for those ones, you can see this one here, because we got A and B, and this one here, we got B and C, and also this one here, we got A and D, and also this one here, we got C and D. And this one here, we are not really considering, because this is just has to do with other kinetic components, which we don't care. We only care about the one that's to do with the current one. All right. So now we got AB, BC, AD, CD over here. Okay. So what do we have? Okay. And these edges would have already been processed, which means they have already been marked as either the tree edge, connecting the edge that will cut, that will actually cross the cut, and also internal edge. Those are the edges that do not actually cross the cut. Okay, and they should also be in the C of U. Okay, so what do we mean by that? Okay, so all these edges you can see AB, BC, AD, and CD, and also all these right here. So what I would do is right here, all the edges with an endpoint that is a member of the cluster of D, right? Either A or B or C or D, right? A or B or C or D. So these are the 4. Okay, let's write them out. It's going to be AB and also BC and also AD and also CD, right? So these are the 4 edges, and then they are processing a different way, right? Specifically, I want to be more precise. You can think about AB. Well, let's look at all these together, right? So at the moment we got ABCD, right? If you go back to the diagram that we had earlier, A, B, C, D, right? So basically, at this point here, this is what we have. And we already got AB, BC, AD, and also CD, right? That's all we got before iteration number 6. That's to do with this particular kinetic components. And for all these edges right here, AB, AD, CD, and BC, right? All of these 4 edges. So these 3, 1, 2, and 3. So these are the ones that used to cross the cut. So these are the tree edges. And this one here will correspond to the no change iteration earlier. And that one there will be considered as the internal edge, because at that point, we are trying to connect C and D, but C and D were already in the same cluster, so we don't really cross the cut, right? And also, most importantly, you can see all these edges have the cost lower than the current one that we are trying to look at, which would be DE right here, right? You can see. Let me say it again. This is the connected components A, B, C, D that we are looking at, right here. And we got 1, 2, 3, 4 edges right here. And for all these 4 edges, their costs are lower than the 5 over here. That's why they would have been processed already earlier, but they might be processed in different ways. For AB, AD, and BC, for these 3, they correspond to like a tree edges from these 3 iterations where we simply try to cross the cut. And this one here corresponds to this iteration over here. So because C and D, they happen to be in the same cluster, so we actually didn't cross the cut. So we didn't merge the cluster. All right. So that's really what this point is saying, right? And now all these vertices, like A, B, C, D, like A, B, C, D, all these are in the same cluster right here. That's what it is saying, right? So this one is really tricky, but let me try to give you the intuition here. We are basically saying, right now, we already got this particular connected component so far in the beginning of iteration number 6. And now we choose the minimum edge that's gonna cross the cut right here, which will be DE right here. And we are saying that all the earlier edges that will be in the same connected components, which will be this, 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 and this, all these 4 edges, their weights guaranteed to be smaller because they're chosen earlier, right? Because they're smaller, they would have been extracted earlier from the priority queue. And also, they might be handled in 2 different ways, either like this, like AB, AD, and BC. They are like a tree edges. They just try to cross the cut, so they will trigger the merging of 2 clusters. And also this one here is not going to trigger any merging, right? That's really what this point is saying. This one is a little bit tricky. You can see it's it's kind of phrased in a very concise way, but you really want to read it through more carefully and also look at the example I'm trying to show to you, right? Especially about iteration number 6, right? Any edge that is not involved in this particular connected component like an E and F, we don't care, right? We only care about what's really involved in the cluster of right here. Okay. All right, let's just go back here. All right, so let's see. I think that's about for this one here. Okay, so the conclusion we can make will be right here. All right, so that means, okay, by the way, this symbol here, that means there does not exist. So there is no. So given that, we try to, so we should look at line number, okay, let me look at these 2 together, right? We look at line number 9, really. Okay, line number 9 is right here. Line number 9 is about extracting the minimum from the priority queue, right? So we are basically saying, let me write it down. So this one here, UV, is the minimum weight edge crossing the cut. Crossing the cut between cluster of U and also everything else, right? And we kind of said that any cheaper edges, any edges with the smaller weights, as we said earlier, they would have been already processed and included in the current cluster of U. Okay, that's something we said. So this one here, it will guarantee to be the minimum. All right. All right, so very, very important for you to actually see this one here. Right, so line number 9, even we know that it's going to be the minimum edge currently, but at the same time, it's also the minimum crossing between cluster of U and also the rest of the vertices. Right, so the final point to really make is, so now we want to link this one to the cut property. Of course, you got to make sure you get yourself familiar with the cut property. So now, since we talk about crossing the cut, so we know that this particular edge, UV, is guaranteed to be part of the minimum spanning tree, right? So that's why over here you can see we could safely, so now just for iteration number 6, given that they are not the same, so no, we know that we can merge, and once we merge, we're actually going to include the edge DE over here as a new edge in the ultimate minimum spanning tree, right, that we're constructing. And we can do this because of the cut property. We are able to just add this into the set we're maintaining. So this one here, safe to include DE in T because of the cut property. All right, it is very important for you to see that one there. Okay, so DE over here. Given that it's going to be a case of the merge because it's crossing the cut, so we're going to include it in the final ultimate minimum spanning tree. But of course, we don't know yet the complete structure for the minimum spanning tree, but we know that at least by the cut property, DE should be a member in that particular minimum spanning tree. So we can keep going until we get to the n-1 edges in total. All right, so that'll be the final point I want to actually talk about, right? It's very important for you to actually go over, this last lecture here is not very long. Well, it's not, it does not cover that many topics. It just talk about the concept about partition, cluster, and also cut, about what you should know about to really understand more about the intuitive correctness of the Kruskal's algorithm. All right, I think that will be it for the last bit of the coverage for the course.